Okay, so today we're going to talk about the central limit theorem, which is part of using the normal distribution in calculating information. And what it does is well, you'll see in a second, but what it allows us to do is for testing purposes, if we do not have normal distribution, it allows us to create normal distribution, basically. So let's just take, for instance, we have a dice roll and we roll it 1,000 times. We should get a fairly uniform distribution of 1, 2, 3, 4, 5s, and 6s. So that if we add it up, we should get an average somewhere around 3.5. Okay, because if we add 1 plus 2 plus 3 plus 4 plus 5 plus 6 and divide by 6, we get 21 over 6, which is 3.5. So here they did a sample, they rolled it 1,000 times, they got an average of 3.41, which is close to the expected average, and a standard deviation of 1.73. Now, that's all well and good, but what happens, notice this isn't normal, this isn't a normal distribution, and we want to be able to use the z-scores to standardize things, so we need to turn this into a normal distribution, and they think, well, how can we do this? And the way that happens is they find out using the central limit theorem that if we can sample sizes, if we take the means of those distributions, okay, and they improve, the bigger and bigger they are, the closer they get to the actual mean, and the smaller the standard deviation gets. So they become more normal. And as we can see here, they did a one dice roll. They got a mean of 3.41 with a standard deviation of 1.73. Then they took 2 dice and averaged those. They got took the mean of those, and they got the mean of those means was 3.43, and 1.21 was standard deviation. And then they did 5 dice rolls, and they got a mean of mean of the means of 3.46. Now so getting closer and closer with a standard deviation of 0.74. Then if they took 10 dice and rolled them, and then they took the means of those means, they got an average of 3.49, and so the means get closer and closer to the expected mean, and the standard deviations get smaller and smaller. And like they said, as we get bigger and bigger samples, we get closer to the normal distribution. Now here's 2 of those graphs. Now when we compare them to the original, we can see that definitely this has more, this has a little bigger, better bell-shaped curve. This is even more bell-shaped, and if we kept looking further and further, we would see a even better and better bell-shaped curves. So the central limit theorem has a couple of pieces. So we have to have many random samples, okay, and we take their means. Okay, so if we take the means of these samples, then the distribution of the means will be approximately normal for large sample sizes. And that for large sample sizes, they mean n is bigger than 30. So when this is useful so that when we do testing, we can say that if we have a samples of bigger than 30, we can assume through the central limit theorem that we're going to be dealing with normally distributed things because they're going to be taking means of those. So that's the first part, that they become normal. The second part is that the mean of the distribution means approaches mu, which is the mean of the population. And that the standard deviation for those things is equal to sigma divided by the square root of n, where n is the number of the sample size. So what we have is we use this here, this square root of n, to find what the new standard deviation would become. We take the standard deviation of the population, divide by the square root of n, and that should be our approximated, that should be what our standard deviation becomes. And so the standard deviation becomes smaller because we're dividing. And so here it is in visual form, that if I have a normal curve, and I take samples of n, I get a smaller normal curve. When I get 10, I get an even more narrow curve. And when I have 30, I have an even more narrow curve. That's perfect. I mean, it's normal all the way down. However, if I have a uniform curve, where everything is uniformly distributed, like our dice rolls. As I take 5, I get a little more normal with some wide standard deviation. Sample size of 10, I have a normal curve with a smaller standard deviation. And as I get to 30, I have a normal curve with almost no standard deviation. If it's skewed, the same thing occurs. As I have a skewed original population, 5, it's still a little skewed, okay, but it's getting closer. 10, it's still a little skewed. The standard deviation is getting smaller. But notice here when I get to 30, I'm still getting a normal standard deviation. So that's the important thing. As sample size increases, we'll get to normal. And when we get to 30 or bigger, we should have a normal curve. So now let's actually use this and see how these things change if we're doing a sample with means or we're just taking an individual. And so here they're saying you're a high school principal and you have 100 eighth graders. You're about to take a national standardized test. And the test is designed so the mean is 400 with a standard deviation of 70. And the scores are normally distributed. All right. That's important for the first question. What is the likelihood that one of your eighth graders selected will score below a 375? So because it's normally distributed, we can look at one student, put it on the z-score, and calculate this out. So we're going to do this right here. So we have that z is equal to the number we have, 370, minus the mean over the standard deviation. And this comes out to be negative 25 over 70, which is equal to negative 0.36. Now we were going to look this negative 0.36 up on our chart. Okay, we have to look up negative 0.36 up on our chart. Remember we had a chart on page table 5.1, which was in page, get it? 211, or we can look on table A in the back of the book. But here, we can look here and we see negative 3.5, well that's close to negative 3, is 36%. So, there's a 36% chance of finding a single student that has a test that is below 375. Now, problem B says your performance as a principal, so whether or not you're going to get a raise, is dependent on how well all of your eighth graders do. So what's the likelihood that you have a group of 100 eighth graders will have a score below 375? So to do that one, we come back here and we still have z. We're still going to be looking at our z table. So we have 375 minus 400 divided by 70 divided by the square root of 100, because we're taking means. This is the mean of a group. So this is going to be equal to negative 25 over, and this is 70 divided by 10, which is 7. And this comes out to be negative 3.57. So we take this negative 3.57 and we look up on our table and see where does that leave us. And negative 3.57 is below this, so we're at less than 0.02%. So that's a tiny, tiny number. We're far out into the range. So that's very good. You as a principal, you have a very good chance of not having these students get below a 375. Which is probably good for you. So here, if we look at our table, negative 0.036 is the 36th percentile, ish. Okay, so about 1 in 3 students will have a test score below 375. But on the second one, a negative 3.57, that's less than I don't know why I wrote that twice, 0.02%. So less than 0.02% of all students, or about 1 in 5,000 chance of this occurring, of having a mean score of less than 375. Okay, so we can see that there's a real huge difference in the variations of these two curves. Okay, now one thing we need to know, in the first problem we needed to know that this was normally distributed, because if it's not normally distributed we couldn't use the z-score. But for the second problem, that doesn't matter because we're looking at means, and the means of means become normally distributed as we get larger and larger groups. So that one doesn't have to be normally distributed when we're doing it. They don't have to tell us that. We don't care. But if it's a single person, we need to know that it's normally distributed in order for this to work.